Suppose that we're interested in comparing the proportions from two different populations. So from some first population, we have a proportion, right? Some number of successes. And from a second population, we have the same thing. And what we're interested in knowing is, are these proportions the same? Are they different in the population, right? So from our samples, we can see what our sample proportions are. We want to know, does this translate to the populations themselves? And so we might be interested in finding confidence intervals for the differences in these proportions, or we might be interested in running hypothesis tests that formally compare these proportions to one another. So in order to conduct statistical inference for population proportions, we can first use the normal approximation to the binomial distribution, and then we can apply normal-based inferential procedures to this. So what does this actually end up looking like? Well, the normal approximation for the binomial, if we start by assuming that x follows a binomial distribution with parameters nx and px, so px is the proportion of success in the population, nx is the number of samples that's being taken, then we can view x as counting the number of successes in nx independent trials. Each trial has independent probability of success, px. We know from the binomial distribution that the expected value is always going to be the number times by the probability of success, so nx times px, and the variance is always going to be nx times px times 1 minus px. Now, if nx is large enough when we compare it to the probability of x, or 1 minus the probability of x, then x is going to be approximately normally distributed. This is what we refer to as the normal approximation to the binomial. And so specifically, x is going to follow a normal distribution approximately, and the parameters of this normal distribution are going to be the same as the expected value and the variance. All right, so we have that the expected value is nx times px, right, and the variance is nx times px times 1 minus px. So these correspond to one another. Okay. Now, if we take the sample proportion rather than x itself, so we're thinking about the total number of successes divided by our total number of trials, right? So in what proportion of times did we see success here? This is also going to have an approximately normal sampling distribution. And specifically, we're going to find that px follows a normal distribution with the mean of the true proportion, right? So the sample proportion is going to be approximately normally distributed with a mean that's equal to the truth. And the variance is going to be px, 1 minus px over nx, right? Where that's all based on the true value of the success here. Now, if we take a second population that we'll call y based on ny and py, then this is going to follow the exact same type of result, right? So we're going to have that the sample proportion of y follows an approximately normal distribution with a mean of py and a variance of py times 1 minus py over ny. Okay. So we can think about then the differences in these proportions, right? So we want to compare px to py, and so one of the natural things to do is to think about, well, what is the difference in sample proportions? So if we take the difference in sample proportions, then using the properties of the normal distribution, we can write that the p hat x minus p hat y is going to be normally distributed with a mean of px minus py, and then a variance that is equal to the summation of the two variances, right? So px times 1 minus px over nx plus py times 1 minus py over ny. Now, this variance term here depends on the idea that x and y are independent of one another, right? And so that's commonly the assumption that's going to be made in this situation. But in that setting, we can take the variance of x, which is this first term here. We can take the variance of y, which is that second term here, and then we add them together, right? And so this is going to be the approximate sampling distribution, supposing that we have a large enough sample size for both x and y. So we require both nx and ny to be large. But then from here, we can use this approximate normal sampling distribution in order to form confidence intervals or to perform hypothesis tests. So critical values and p-values can be obtained using the normal distribution because we have this normal sampling distribution here. So what does that process of forming confidence intervals or hypothesis tests actually look like? Well, to take a confidence interval, first we can say, well, px minus py, right? This is our estimated proportion, so p hat x minus p hat y is going to be plus or minus z alpha over 2, which is our critical value from the normal, times by the square root of the estimated variance that we have here. Right, so the square root of the estimated variance gives us our standard error. So we're plugging in the estimates for p hat x, and we're at p hat y. Right? The sample size of x, the sample size of y, all of that remains the same as it is in the formula. And this is going to give us an approximate confidence interval for the difference in these proportions. Z alpha over 2 is the standard normal critical value. In the standard error, where we have p hat x and p hat y here, both of these can be replaced by 0.5 if we want to be as conservative as we can be. And so the idea there is that the standard error here, while we're estimating it sort of more correctly using the values that we've estimated in our sample, if we want to make sure that our standard error is not an underestimate of the truth, plugging in 0.5 for p hat x and 0.5 for p hat y is going to lead to the highest possible standard error in this context. And given that it's the highest possible standard error, that's going to lead to the widest possible confidence intervals. So sometimes we want to make sure that our results are conservative, and so we plug in 0.5 rather than our estimates. We can use this same procedure to fit one-sided or asymmetric intervals as well by changing out what is the critical value that we're actually using here. So picking different critical values will lead to different forms of our confidence intervals. Okay. Now for hypothesis testing, we can think about sort of the similar setup that we have going on here, right? And so in this context, for instance, we have the null hypothesis is that x minus py is going to be 0 versus the alternative that these are non-zero, right? And so this is going to be a sort of standard hypothesis that we might want to test here, right? What do we need to do? We need to take our z-score test statistic. So we take p hat x minus p hat y, right? The difference that we have been dealing with this whole time, and we divide that by the standard error under the null hypothesis. And so when we're doing this, we get divided by the square root of p hat times 1 minus p hat times 1 over n plus 1 over m. And if the null hypothesis is true, this should follow a normal 0, 1. Now, importantly, we can ask ourselves, well, what is this p hat here, right? And p hat is going to be given by our total proportion. And so what do we mean by that? Well, p hat is going to be the number of successes in x plus the number of successes in y divided by the total number of trials that we've run between x and y, so nx plus ny. Okay, and the idea is that if px minus py is equal to 0, then what we're really saying is that px and py are exactly the same, right? They are equal to one another. And so the idea is that p hat here is going to serve as our common estimate for both p hat x and p hat y, right? We're going to say, well, if they're really the same, if the null hypothesis is true, well then p hat x should equal p hat y. Right, and so we just estimate a single one, and then when we combine this variance together here with a common variance estimate, we'll be able to factor out what we have in the numerator over here, right? So we can factor this out, we can factor this out. That's going to become our p hat times 1 minus p hat, and we're left with 1 over n plus 1 over m, where m here is our alternative notation for the sample size of y, right? So m and ny are going to be equal to one another in this case. You will see both notations commonly used, and so we can write here that just m is equal to ny, okay? And so the idea is that you take the common estimate, you plug this in to our standard error formula, and then everything follows from there. Importantly in this situation, which this differs from other types of multi-sample hypothesis tests, we can only test the hypothesis that the difference in proportions is equal to 0 versus the alternative, that it's not equal. We can do this with one or two tailed tests, so we can test directionally, is it less than or equal to 0, is it greater than or equal to 0, but we can never test it being non-zero. And the reason for this is because the approximation that we're using here is really not particularly good if we have these differences being non-zero. We can work out some approximations, they become a lot more complex to do, but typically if we want to test a hypothesis that's not the proportions being equal to one another, then we're going to want to look to other methods to do this. Okay. Once again, just like in the case of the confidence intervals, if we're hypothesis testing and we want to be as conservative as we can be, we can take p hat equals to 0.5, and that's going to lead us to the most conservative test results. So we can take a look at an example of how this might actually be implemented in practice. And so suppose that we wish to determine whether we have two coins that were equally fair, so whether they come up heads the same proportion of time. We flip a quarter 50 times and we find that it comes up heads 22 of those, and then we flip a dime 75 times and find that it comes up heads 40 times. So in this case, we want to find a 95% confidence interval for the difference in proportions, and then we want to answer, are these two coins equally likely to show up as heads? Okay, and so it's worth us taking a minute to write down what are we actually given here. Okay, and so we have x is going to be equal to the number of successes on our first coin, so that's 22, right? And then we have nx is going to be equal to 50, right? And again, just to share both types of notations, sometimes you'll also see this written as simply n. Okay. We are going to have y being the number of successes on our second coin, so that's going to be 40. We have ny is going to be 75, and again, sometimes we will write this out as m. Okay. And so if we wanted to know, well, what is our proportion of x, right? That is going to be 22 out of 50. Our proportion of y is going to be 40 out of 75. Okay. And so now here we could also ask ourselves, well, what is the common variance going to be, or what is the common proportion going to be, rather, right? And so we can take p hat is going to be the common proportion, and that's going to be our total successes, 22 plus 40, out of our total number of observations here, 50 plus 75. Okay. And so then into each of these cases, we will take our proportions and we'll plug in the relevant results, right? In the first case, we need to work out, well, what is alpha going to be? Remember, alpha is always 1 minus our confidence level. So 1 minus 0.95 gives us 0.05, okay? And so then we're going to be dealing with z of alpha over 2, or z of 0.025 in this case. We plug into our confidence interval formula and go from there. In the second case, we're still dealing with an alpha of 0.05, and so that's going to be the relevant comparison for the p-value that we calculate. Okay, and so we can walk through how all of these calculations end up playing out here. Okay, so we have x being 22 and x being 50, so then the proportion is 22 out of 50, or 0.44. Similarly, y is 40 and y is 75, and so then if we take 40 out of 75, we get 0.53 repeating. Now, through the normal approximation, what we know is that p hat x minus p hat y should be approximately normal, with the mean difference being the mean is the difference in the true proportions, and the variance is the sum of their two variances here. Okay, and so we want to find a 95% confidence interval, and so 1 minus 0.95 gives us alpha, and that's going to correspond to a value of 1.96. If we want to figure out, well, how does that 1.96 come out, we can run Q norm in R, and Q norm of 0.025, because 0.025 is 0.05 divided by 2, right? So Q norm is always going to give us the critical value of the normal, Q standing for the critical value, norm for the normal, right? And so this tells us that this is going to be the 1.96. And now we can plug all of this into our formula for the confidence interval. So doing this and then simplifying down, right, we get our difference in sample proportions plus or minus our critical value times by the square root of that variance. So we plug in our proportions here, that critical value of 1.96, the proportions sample sizes over here, right? And all of this works out to being an interval of negative 0.271 to 0.084, right? So that is our 95% confidence interval for this difference in proportions. So for part B, are they equally likely to show up heads? Okay, so we can run this as a hypothesis test. Note that the hypothesis that we're testing is under the null, the difference is 0. Under the alternative, the difference is not equal to 0, right? And so this is always going to be a 0 on the right-hand side here. In this case, we are looking at that two-tailed alternative. Okay. So we calculate that common proportion, adding up x and y, adding up their totals. That gives us 0.416 as our common proportion here. And then we can ask ourselves, well, what is the observed value of our test statistic? So we take p hat x minus p hat y, divide that by the square root of our estimated variance, right? So that's p hat times 1 minus p hat, 1 over n plus 1 over m. And so we work out what is the difference in our proportions here, plug in our 0.416, our 50, and our 75, and that leads to a test statistic value of negative 1.037. So now we can work out, well, what is the p-value in this case? The p-value, because this is a normal-based p-value, is going to be 2 times the negative version, which is already the negative 1.037, where this is all plugged in to our normal CDF here. Of course, to get this, we would need either a table or to use statistical software. And so if we wanted to use R, we can compute this as 2 times p norm of negative 1.037. Here, the p standing for the probability, right, which is what we want with phi. And so phi and p norm are the same function. And if we actually calculate this out, we find a p-value of 0.2997. Okay, and so what is our conclusion here? Well, since the p-value is larger than the level of significance, we fail to reject the null hypothesis, and there's insufficient evidence in the sample to conclude that the proportion of heads from the first coin is any different from the proportion of heads observed from the second coin. Now, it's important to note that we could have actually gotten this directly from the confidence interval itself. If we notice that the confidence interval contained 0, then that's a confidence interval for the difference in proportions. And so if we're going to test, is the difference in proportion 0, because that's in the confidence interval, we can immediately say that we're going to fail to reject the null hypothesis. And so we didn't actually need to run through the hypothesis test in this case, but it's useful to do in case you had wanted it at a different level of significance, in case you don't actually care about the confidence interval, and so forth. Okay. We also could have made this process conservative by taking the proportion to be 0.5 in the standard errors in either A or B, right? And so this would have either led to a more conservative confidence interval or a more conservative hypothesis test. So we can take a look at a second example here. In this example, we have a company that is concerned that their hiring practice may suffer from unconscious bias. So they want to decide whether qualified male applicants are hired with different frequency than qualified non-male applicants. Okay, and so over the past year, from the same position, the firm hired 45 out of 100 qualified male applicants, and they hired 18 out of 72 qualified non-male applicants, right? And so we're restricting our focus here to just those individuals who are actually qualified applying for a job, and we're seeing that 45 out of 100 of the male applicants were hired, where 18 out of 72 of the non-male applicants were hired. And so we want to do a similar thing here. We want to form a 99% confidence interval for the difference in proportions, and we want to test the hypothesis that the frequency differs with alpha equals 0.05. Importantly, in both cases, we want to do this conservatively. We want a conservative 99% confidence interval, and we want to test conservatively here. And so remember, whenever we're dealing with the conservative proportions, we're always going to be taking the estimated proportion to be 0.5 in the standard error estimates. And so again, just taking stock of what we have here, right? We have observed a value of x equals to 45, nx, which again we can write as n, is 100, y we've observed as 18, ny, which we can write as m, is going to be 72. Okay, and so then we have p hat x is equal to 45 out of 100, and we have p hat y is equal to 18 out of 72. Now, in this case, we're not actually going to need to take a common p hat, right? Because we're just going to take this value to be equal to 0.5 in order for us to be conservative here. Okay. When we want to find alpha for our first confidence interval here, we are going to take 1 minus our confidence level. That gives us an alpha of 0.01, and so then we're going to want z of 0.01 divided by 2 as our critical value. In terms of the hypothesis test, we are testing the null hypothesis that the difference in proportions is equal to 0 versus the alternative that it's non-zero, right? They are interested in seeing, are these hiring rates equal? Not, is one higher than the other specifically. Okay, and so we can take all of this together along with the actual values that we've been given and run through calculations of this hypothesis test and of this confidence interval. Okay, so we've pulled out our observed data. We form alpha, which is 1 minus 0.99, so 0.01. This is going to lead to a critical value of negative 2.58. If we want that critical value, we can use R. Using the Q-norm function, we plug in 0.005, and that gives us our negative 2.58 here. Now, in order to make inference conservative, we take 0.5 in our standard errors. And so what does this actually turn out into? For our formula for our confidence interval here, we have our difference in sample means, critical value, and then when we're going to be plugging into p hat x or p hat y in our standard error, we plug in 0.5 for both. Okay? And doing this leads to a confidence interval of 0.001 to 0.3999. Right? And so that is going to lead us to the estimated difference in proportions, the confidence interval for the estimated difference in proportions. Taking a look at part B, now we need our hypothesis test. So again, recall that we are testing whether the difference in proportions is 0 versus it being non-zero. Okay, and so we calculate out our test statistic, p hat x minus p hat y in the numerator. The denominator is going to be the square root of p hat 1 minus p hat times 1 over n plus 1 over m. And so we take our differences in the estimated proportion. We've plugged in 0.5 here because we are trying to be as conservative as we can be. Okay, and this leads to a value of 2.588. Okay, so if we want to get our p-value out of this, we're going to take 2 times the negative version of that plugged into the normal CDF. Using R, we can get that as 2 times p-norm of negative 2.587, which gives us a p-value of 0.0097. Okay, and so we're testing at a significance level of 0.05. Since our p-value is smaller than the level of significance, we're able to reject the null hypothesis. We conclude that there is sufficient evidence in the sample to conclude that the proportion of qualified males, which we observed to be 0.45, is significantly different from the proportion of hired qualified non-males, which we observed to be 0.25. Okay. So using the normal approximation, we can conduct statistical inference regarding the difference in population parameters. Because each population parameter, population proportion, is going to be approximately normally distributed, the difference is also going to be approximately normally distributed. And so we can take that result and conduct statistical inference on those differences of proportions. Now, this is going to be approximate inference, and it relies on the sample sizes being sufficiently large. Moreover, when we're actually running this approximate inference here, in the hypothesis testing case, we have to be careful and note that only some hypotheses are actually going to be able to be tested. And so if we want to test specific hypotheses, this approach is not going to work. However, most of the time we're going to be interested in saying, are these proportions equal or are they not equal? And in those settings, we can run through this procedure exactly. And so the normal approximation to the binomial is going to be useful for us conducting inference for 2 binomial proportions.